So in the previous video, we saw how we can scale our databases using horizontal and vertical scaling. In this video, let's see how we can keep our databases highly available. I hope you're ready. Let's get started. Welcome back, engineers. So previously when we discussed distributed systems, we saw how we can separate out the database layer from the web server layer so that they can scale independently, right? So we scaled the web layer by adding more web servers, and we saw how we can scale our database layer by adding more shards and distributing the data across multiple servers. But we haven't discussed the availability aspect of it. So in the case of single database server or in the case of sharding, these are still independent and single database servers, right? So when this shard one goes down, this part of data is lost and this cripples the entire system. In the case of a single database server, if this database is lost, then there is no way to recover from this and the entire system is crippled. So how do we make the system highly available? So how do we do that? So instead of relying on one database server, we will now rely on multiple database servers. So we distribute the responsibility between multiple servers. So there are different ways to do this, and one of the popular ways is to use the single leader replication system. So this is how it works. So instead of having one server, we will have multiple servers, and among these servers there will only be one leader, and this leader will forward all the requests to the followers. And this leader is responsible for taking in all the write operations, which includes insert, update, delete, and whatever, anything that changes the data. So the leader is responsible for changing the data, and once it receives this data, it can forward the same request to the followers. So there can be multiple followers, and for each write, update, or insert, the same request is forwarded to multiple followers and they keep the data up to date. So this is how the leader follower system works, right? So this is also referred to as master slave system. So there is only one master and the remaining servers are followers or slaves. So how does this help with high availability? So when the leader goes down, one of the followers will become the leader and will be now responsible for taking in all the writes and forward all the requests to the remaining followers, right? And when the server that went down comes back, that server can go back to being a leader, or that server can become a follower until the next cycle, right? So that way we can keep our system highly available. So this is how a single leader replication system works. And because we have multiple servers, and because they are available, they are up and running, and they have the same configuration as a leader, we can also make use of this to achieve load balancing. So how can we do that? So since the leader is taking in the responsibility of handling all the writes, the followers can be used to achieve reads. So the followers can take the responsibility of providing the reads. So the web servers can talk to the followers for read operations, read queries, and they can talk to the leader for achieving the write queries. So at any point of time, there is only one server that is responsible for handling the writes and distributing the writes to the followers. So this is how the single leader replication system works. Now let's see some other aspects of this single leader system. So far we have discussed what is database replication. So this is nothing but keeping copies of data. Okay. And there are multiple ways to do this, and we are discussing single leader system. And in single leader system, there is always a leader and there are multiple followers, like this. Now let's see how the replication happens. So first is a synchronous method, which means that for every operation that needs a change, like an update, the update needs to go to follower 1 and follower 2, and the leader is waiting for the confirmation of the followers before giving it back to the client that the update is successful, right? So it is tightly coupled with the followers, and it is waiting for the confirmation from the followers before responding to the client. So this is synchronous replication. But there is a problem with this, because even if one of the followers goes down, the leader is stuck. It is waiting forever for the follower to come back, and it is no longer accepting any further writes. So the entire system is crippled. The other way to do this is asynchronously, which means that leader just forwards the request to the followers and forgets about it and continues to take in new writes. This way we can keep the leader highly available for taking in more writes, and the followers can eventually update themselves. And this type of process is called eventual consistency. So in this scenario, the leader is not stuck and can keep on taking the write operations from the client. So this is asynchronous. But the problem is, because we are using the followers for read operations, the follower might be giving out stale information. So it has not yet updated the information from the leader, but it is giving out some stale information. So that way we have lost a little bit of consistency, but we have achieved high availability for the leader because it is no longer stuck. So the balance between these two is semi-synchronous. So in this, we are finding a midway between these two scenarios. So let's say we have leader and follower 1, follower 2, and whenever there is a write coming in, the leader forwards a request to follower 1 and waits for confirmation from follower 1. So this way the leader and follower 1 are always in sync. And F2 can be asynchronous. So this way we can achieve consistency with these two. So we know that if leader goes down, at least one of them has the latest data, and follower 2 can be asynchronous, which means this will be eventually consistent with the main data. So this is kind of a balance between synchronous and asynchronous, which is semi-synchronous replication. So the advantage with synchronous replication is all the systems will always be in sync, and this gives us great strong consistency. But the problem is if one of them goes down, the entire system is stuck. And with asynchronous, we can keep the leader not stuck and keep it available for new writes, but the followers can give out stale data before they are updating themselves, right? Because it is asynchronous, they can go down and they can come back up, and then they might be needing some more time to update themselves, and during that time they can give out stale data. So the balance is using semi-synchronous replication, right? So we can achieve at least some level of consistency between the replication set. Now let's see how failover works. So what happens when follower is down? So we have leader F1 and F2. Let's say our F2 is down. So what happens now? So the leader was sending all the writes to F1 and F2. Now it no longer sends the writes to F2 because there are heartbeat checks happening between the replication set, and F2 is no longer available, so writes need not be sent. And when F2 comes back up, it recovers from the last known state and takes in the new logs from the leader and updates itself. So this will become eventually synced up with the latest updates, and the leader can start sending out new updates to the follower too. So this is what happens when follower fails. Now let's see what happens when leader fails. So when the leader fails, so we have leader F1 and F2. When the leader fails, one of them needs to go and become a leader. So how does that happen? So the simplest way to choose a leader is checking the logs of these two followers, right? So whoever is having the latest updates can become the leader, can be promoted to be the leader, and that leader can now take in new updates from the client. Another way is to use some kind of a voting mechanism to choose a leader, and that is something we will discuss later when we are discussing consensus, right? So to keep it simple, let's understand that whenever a leader goes down, so one of them becomes a leader. Depending on the logs, whoever is having the latest updates can become the leader. Now let's see what happens when we are adding a new follower. Now so far we have seen leader with 2 followers. Let's say we want to add a third follower. So we have F1, F2, and let's say we want to add F3. So when a new follower is introduced, this follower will take in the latest snapshot of the leader and keeps updating its database with all the changes that have happened so far onto the data, right? So this includes all the write operations, update operations, inserts, and deletes and everything. So up to the snapshot, this F3 follower is up to date. So after the snapshot update is completed, it can start receiving the logs to keep itself up to date until real time. Once it is available, only then can the leader start sending new writes to this. So when a new follower is introduced, it needs to catch up to the latest changes and then informs the leader that, hey, now I'm all caught up, you can start sending me new updates. And then the new updates are being sent to the new follower. So that's how the mechanism goes. So I would like to pause here because there is a lot of topics that we have covered so far, and let's keep it as part one. So in the part two of this series, we will discuss what exactly happens during the replication, what kind of logs are being sent, and what are the problems that are commonly faced in single leader replication systems, right? So we'll see all that in the next video. Thank you so much for watching until this point. Do leave a like if you found this helpful. I'll quickly see you in the next video. Cheers.